Okay, so today we're going to talk about combinations of functions, which is essentially just a way that we can perform operations with functions. So I can add them, I can subtract them. So if we do the sum or the difference of two functions, you're going to see the notation in this format here. So it's going to look like f plus g at x, which really just means f at x plus g at x. And if you see f minus g at x, it really just means f at x minus g at x. We can also use something called the superposition principle in order to graph. And basically what that means is we just find a similar set of x values for each function. And if I'm adding the functions, I'll just add those two functions' y coordinates. So x's will stay the same and I add the y's. Or if I'm subtracting the two functions, I'll have a similar set of x values for each. I'll have their y values and I'll subtract their y values. So just as an example here for you guys, we have f at x equals negative x squared plus 3. And g at x equals negative 2x. We want to determine the graphs of f plus g at x and f minus g at x. So just to remind you, f plus g at x is really just equal to f at x plus g at x, and f minus g at x is really just equal to f minus g at x. Okay, so notice that I have the same set of x values for each of these functions here. What I would like to do quickly here is I want to get the corresponding y values for f at x for these x values here. So we're going to take each of these x values and plug them into f at x for x, find out what the y is, and record that information here. And we're going to do the same thing with g at x. So we're going to take these x values, we'll plug them in for x at g at x, and record those values here. Okay, so I'm going to give you guys a second to do that. Find your y values for each function here. We'll pause, and then we'll fill out the last two columns. Okay, numbers for the first column, negative 6, negative 1.
2, 3, 4, 7, 12.
Did everybody else get this?
Yeah.
Did you say no? Did you get that, Annika and Alexandra? No, you guys did that one. Yeah? We're all good? Okay, g at x?
6, 4, 2. 6, 4, 2, 0. Negative 2, 4. Negative 6.
Perfect. Okay, so for f at x plus g at x, yep, sorry.
It's easier for f at x plus g at x just to do negative 6 plus.
Yeah.
Instead of like doing it like here, it's one that plus g. You know what I mean? Like,
Sorry.
Like you said, f plus g times x is the same thing as fx.
It's not times x, it's f plus g at x, right? It's just function notation. So I'm just saying that that is equal to this. Okay, so what we're going to do is x coordinates always stay the same. Those are consistent across everything that we're doing here. For f at x plus g at x, we're going to take f at x, the y of f at x and the y of g at x, and add them together, okay, to do the sum of the functions. So we're going to get, 0, 3, 4, 3. Great. Okay, so before we do f at x minus g at x, we're going to graph these points. So the first graph that I'm going to do is these x coordinates with these y coordinates. That's the sum of the two functions. That will be the resulting graph if I take those two functions and add them together. So I'm going to graph the point negative 3, 0. I'm going to graph the point negative 2, 3. So these are the x's for everything, and I'm graphing these y's. Okay, negative 1, 4, 0, 3, 1, 2, 2, 3. Doesn't really make sense. 3, 6.
3, what? I got 0.
You got 0 right here?
0, 3, no. Yes, I got negative 1, negative 6. Like it's a quadratic.
Okay, one person at a time, William. Okay.
Yeah, it's a quadratic. It's a quadratic, so it's at 0 it's 3, and then it's 1 at 2.
Okay. So we have to fix this. So 2, -1, and 6. Yeah? Okay. And -6. Okay, so that changes this, right? Because we have to do -2, +2, -1, -4, and -6 and -6. That's -12.
Sorry, everybody.
Jeez. All right, so we've got, all right, where did we stop here? 0, 3, 1, 0, 2, -5, and -12 doesn't fit. And I'm willing to bet that -4 is also down at -5.
How much you gonna bet?
Bet you $1 million. Okay, so here is f plus g at x. All right, so the resulting function that we get here is actually a quadratic. Let's see what happens when we subtract these two functions. So I'm going to take, in particular, when you subtract, the order is actually important here because we're doing f at x minus g at x. I want to take the y's of f at x and subtract the y's of g at x to get my resulting points over here. Okay, so we're going to do -6 minus 6, -1 minus 4, 2 minus 2, 3 minus 0, 2 minus -2, 1 minus -4, and 6 minus -6 gives us 0. Okay, so when we graph these points, we're going to take the original x values. So notice the x values are not changing at all for any of this. And we're going to graph those with the new set of y values that we got from subtracting the functions. So using these as our x coordinates again, and now we're going to graph these on the second graph here. So we're going to graph, well, 3, -12, -3, -12 doesn't fit. So we'll do -5, -2, -5. We will do -1, 0, 0, 3, 1, 4, 2, 3, 3, 0. And my guess is that we have a reflected point over here at 4, -5 as well. Use the same x points, yeah. X points aren't changing. These are all y coordinates that we're using here. Okay, so here's the next question. Why do the sums of those two functions and the differences of those two functions give us quadratics resulting from that? Let's take a look at what's actually happening algebraically. So we'll take our function f at x, and we're going to do f at x plus g at x and see what happens here. Okay, so let's take a look at f plus g at x. We said that's f at x plus g at x. And f at x was -x squared plus 3. And g at x was -2x. So when we do this and rearrange it, what do we get from the sum of those two things? We actually get a resulting equation where we have a quadratic, and we can see that it opens down in front. So if you were doing the algebraic method, you can graph the function as usual. So maybe we'll use like the same -3 to +3. Okay, and then you would basically be plugging your points into your new function here. Okay, we pretty much have already done this because we've already found the points above, so we're not going to take the time to recalculate them, but you would find if you plug them into your resulting algebraic model that you developed here, that you would get the same x coordinates that we got above. So you'd be getting 0, 3, 4, 3. And then, what did we have? 0, negative 5, negative 12. Okay, you could also create kind of like a quick sketch of this as well by just factoring it and finding the x-intercepts, plot your vertex and your y-intercept as well.
Why did it go from x cubed to x squared? Above.
It didn't.
Oh, sorry.
That's okay. Okay, so same function that results from this. That would give us f at x plus g at x, or f plus g at x. Okay, and then if we look at f minus g at x, we know this is equal to f at x minus g at x. So we would take our function f at x and subtract our function g at x. So what ends up happening here is we get kind of a similar equation, but now it's plus 2x this time. So we get negative x squared plus 2x plus 3. And you can also kind of factor this to create a sketch, or just common factor that negative. So we can see we have a similar quadratic to what we had before, still opening down, but it's slightly shifted in a different direction. So if we chose some x's like the x's above, and we plugged them in to our function, we would find we actually get the same x's in this algebraic model as we do from taking the x's from the first two and taking their y's and subtracting them. So we actually get the exact same x's that we got up here. Okay, and then we would get the same function resulting from that as well. So this one doesn't really fit, but we can graph.
Where are you getting all these points from?
Just plugging them into the function. Okay, so I'm just saying if we took these x's and plugged them into our new function here, we'd actually get the same y coordinates that we got above. So they're going to give us the same y coordinates. I'm copying it out. You guys can check it on your calculator if you want. But yeah, we get the same resulting coordinates here. Okay, so these are just two different methods to graph the same things that we graphed above, right? I mean, negative 3 to positive 3 gives us kind of like a good spread of points usually. You can also kind of just choose to base it around your x-intercepts like we've done previously in our like reciprocal functions. So you could base it around like negative 3 and positive 3 for your subtraction one, and negative 3 and positive 1 for your addition one if you want. Like if you want to just like factor this and find the x-intercepts, you can build your table of values so that you have those x-intercepts in there. Pardon? So you would have to factor this. You'd have to figure out two things that multiply to negative 3 and add to 2, and then get it into factored form. Okay? So if both of your functions have a domain of all real numbers, then your resulting functions from adding them or subtracting them is also going to be all real numbers. But if I have a restricted domain for one of my functions, then the sum of the functions or the difference of the functions is going to be kind of where those domains intersect. So I can't have a domain in my addition function past the domain of one of the other functions. So if one of the functions cuts off, that's kind of going to be the cutoff of my sum or my difference function as well. Okay? Any questions, Pierce?
I'm so sorry, I wasn't able to copy everything now. Do you mind scrolling up just a
Yep.
little bit? Thank you.
Is this high enough?
Do you mind going a little higher? Thank you, yeah, sorry.
Here, I'll zoom out a little bit too. Hammond's throwing desks again.
Goes what class is behind it?
Mr. Hammond's class.
I'm gonna have a fun time.
Are you saying you want me to start throwing some desks?
Yes.
Try it out.
Of course.
Can you pick them up though? Oh, question. Okay.
Here.
I'm kidding. I just picked it up. Oh. One hand. Oh. If you can pick up that whole desk, that would be good.
Yeah, there's like cords that are attached to it, so best not to.
They're gonna rip them out of the wall.
That's so like.
Can I throw a desk?
No,
I didn't hear a no.
I.
Yeah, I did. Yeah.
Okay. It's okay. All right. So that's sum and difference. So either you kind of develop a table of values for each function and add with the table of values or subtract, or you can develop an algebraic model for the single function, for the addition or the subtraction, and make its own single table of values. We're also going to do product and quotient of functions. So when two functions are combined with a multiple or a division, essentially it's kind of very similar to sum and subtraction. So f times g at x is equal to f at x times g at x, and f divided by g at x is f at x divided by g at x, okay? So if f at x is x plus 1 and g at x is x squared plus 5x plus 4, we're going to determine an equation for a graph of f at x times g at x. So f at x times g at x, we said, or sorry, f times g at x is equal to f at x times g at x. Okay, so we're going to develop an algebraic model for this. And a lot of times at this point we are inclined to FOIL this out. But if I'm going to graph this equation, I actually want to get this fully factored. So are there any two things that multiply to 4 and add to 5? 4 and 1, yeah. So I'm going to factor this. This is going to help us to get an equation that will allow us to graph this polynomial here. So I have zeros at -1, and that one's an order 2. Great review for us from our earlier polynomials unit. And -4, it's an order 1. Okay, if you input 0 in for x, you'll actually get the y-intercept as well. So what happens when we enter in 0 for x here? What do we get for a y-intercept? We would, yes. We would get 1 squared times 4, and that would give us 4. Talk to me about degree of this polynomial. What's the degree?
How did you find the y or something?
Just sub in 0 for x into your equation. Alexandra?
The degree is 3.
The degree is 3. How did you know?
Because you add the orders, so 2 plus 1 is 3.
You add the orders? Yep. We can also see here if I have a linear times a quadratic, that's going to give me a cubic, right? How about leading coefficient? What would happen if I did x times x squared? What would my leading coefficient be there? Well, that would be the x cubed term, yeah. But what's the coefficient of x cubed? It's just 1, right? So our leading coefficient in this case would be positive if we went the FOILing route on this first line here. So leading coefficient's positive. What does that tell me about end behavior? Odd degree? Okay. Right, so opposite end behavior going up in the positive direction. So Alexandra's correct, quadrant 3 to quadrant 1. Awesome. Okay, so if we plot our points here, I've got something kind of going like this. And since this is a cubic, it should have something kind of relatively symmetrical going on here. So We're going straight through this because it's order 1. And then this guy's going to go up and back down and around. Sorry, this is actually bad. I'll fix that. We're going to go up and around and bounce off of -1 because that's an order 2. Okay? So it has kind of like a point of symmetry around here somewhere.
Can you get the y-intercept again? I can't.
Just sub in 0 for x.
How do you know which one to do it to?
You can do it to either this or this. It's the same function. Okay? So it should make sense if I'm multiplying something that's linear by something that's quadratic, that my result is a cubic. Right? That makes sense? If I did a quadratic by a quadratic, I would get a quartic, degree 4. Any questions on this one? Can I scroll? Are we all okay? Pierce, do you need a second there? You're good? Okay. Okay, how about the division of these two functions? So in this case, I'm going to take f at x and divide g at x. Order is also important here when we're talking about division. I want f at x to be at the top of the division, and it's divided by g at x. So in this case, what's our f at x? X plus 1 divided by x squared plus 5x plus 4. And I'd like to get this into factored form. So we know whenever we're working with rational expressions, it's always good to see like what the restrictions are and see kind of what's going on here. So same factoring as before. And I do have some restrictions here. What are my restrictions? -1 and -4. Now, the 1 and 1 here will cancel, leaving us with 1 over x plus 4. So we have two different types of restrictions here, one that got canceled and one that remains in the final answer. We talked about this like a couple times in this course. What are each of these restrictions? You guys remember? One of them is an asymptote, a vertical asymptote. What's the other one? Undefined point. Good. Do you know which is which?
The one in the equation is the asymptote.
Yeah. So this is going to be a vertical asymptote, and the -1 will be an undefined point when we graph it. Okay, good. So we know where our vertical asymptote is. That's the 0 of the denominator as well. This is number over function, right? Reciprocal, right? So usually the process that we use to kind of graph these guys is we'll graph the function or create a table of values for the function x plus 4. And we're going to center it around the 0 of that denominator. So I want at least maybe a couple points on each side here. Okay. We're going to plug them each into our x here, and then we'll just reciprocal the y's quickly, okay, to get our 1 over x plus 4. So just plugging each of these in, we get -2, -1, this one's 0, and then 1, 2. And then to get 1 over x plus 4, we talked about just doing the reciprocal of the y's. So x's stay the same. Y's get reciprocaled, -1/2, -1. Remember, this is a vertical asymptote. 1, 1/2. Okay, this is a line. What do we need to remember about lines that get reciprocaled, or any functions that get reciprocaled that have infinite end behavior? What do I also have for my new function here? We have a horizontal asymptote at y equals 0. Can somebody explain to us why this happens with infinite end behavior? Sorry?
Sometimes there's like a function Because every time it becomes divided, it gets infinitely closer to 1.
Right. So if something has infinite end behavior and it's going off toward really high numbers or really like big negative numbers, when I do the reciprocals of those, we get really, really, really tiny numbers. So they all start to approach the value 0, but they never reach 0, right? Because we'll just keep doing the reciprocal of bigger and bigger numbers. That's going to get closer and closer and closer to 0. So we end up with this asymptote along y equals 0. Okay, so we've got that horizontal asymptote. We also have a vertical asymptote at -4. And we're just going to graph our points here, -6, -0.5, -5, -1, and -3, 1, -2.5. Oh, sorry, I graphed -3, 2. All right, so that looks to me like we've got kind of a, oh, sorry. Got a graph that curves around like this. And at -1, remember we have an undefined point. So this is probably going to be like just penciled in as like just a little hollow point there. So you can sub in -1 to figure out what exactly that value is. I'm just seeing if I plug in -1 here, I get 1 over -3. So I put it, 1 over +3. So I put it approximately at 1/3 here. Just a hollow point, yep. Everywhere else on that graph other than -4 is defined, right, for x. The line doesn't actually touch it, it just kind of like hops over that point. Yeah, it's going to get super, super close to that point. As soon as it gets to that point, it's going to just hop right over it. Yep.
It's so hard to like know what is.
I know. Okay, so when I do division, I get kind of a new domain that emerges from these functions because I'm putting a function into a denominator. So this is asking us to state the domain and range of both functions. Let's take a look at f times g at x. What did you say, Fayak? For domain?
Yeah. Or am I wrong?
I don't know. Do you guys agree?
Except for, yeah, restricted.
Well, we're talking about this guy right now.
Oh, that one.
Does this function have any restrictions here? Claire says yes. What are the restrictions?
-4.
Well, those are x-intercepts on my graph. You're saying those are restrictions? Is there any x value that I'm not allowed to enter in just to like a regular like polynomial? Okay, what about the range on this guy? X?
Maybe y.
Y, right? So this goes forever upward and forever downward. There's no asymptotes or undefined points or anything like that that we have to worry about. So the range for this function is also all real numbers. You guys can also use interval notation, -infinity to +infinity with round brackets, right? Okay, now this one's a little bit different because we do have restrictions. So what do we need to say for domain here? This is the multiplication one, yeah. Jonathan?
X can be any range as long as it's not -4 or 1.
Right.
-1.
-1 and -4 are restrictions. I guess I'll put those in lowest to highest order. And the range for this one?
You mean the range except for 0.
What's that?
It can be any range except for 0.
So we would say just y cannot equal 0 for that one. So you can also say negative infinity to 0 in union with 0 to infinity. Okay, so just showing you guys the interval notation for these. I personally think that this method is a little bit easier than doing 3 intervals like this, but whatever you feel comfortable with. You just have to remove -4 and -1 from your set. Pardon?
This is for the other one.
This is for f divided by g, yeah. Okay, so especially when you do divisions, you're probably going to have some restrictions because you're putting a function with x's into the denominator, unless it's a constant function. On your homework, you guys have a little section here where you have some graphs where you have to do the sums. You can just use the points on the function to create a table of values and sum them together. Really, you can only do from here to here. So you won't be able to go past the domain of g at x, right? So you'll really only be able to do the sum from left to right of where g at x starts and ends. Okay, but you can do it similarly to how we did the first question.